Hello and welcome back. Now, in the last study, we have seen that our basic model, which we start with, basically is not too bad considering the training data set, but if you take a look at the test data set, it really messes up, right? So it's not really good. So let's actually try to improve this model. At first, let's start with, let's say, the first convolutional approach. So let's call it, let's say, this is the conv approach, or let's say convolutional, okay? Let's call it convolutional neural net type 1, call it type 1, okay? Because it's our first try, and call this actually, let me actually cover that, Control C to copy that and paste it also there. So if I go in here and put that here as well, right? Convolutional, but this is the, let's say, the basic, basic neural network approach, call it approach, okay? Approach like that. Of course, it's always best practice, as I mentioned before, just write a few additional information in case you want to show this notebook then to another person and he or she does not really know what's going on. That's why it's always helpful to comment as much as you can. So type 1, let's call type 1 approach, okay? Approach like that. So pretty basic, my comments here, I know, but of course, as I said before, just do it the way you need it, okay? So we got this, and now let's actually start with the first convolutional network. Okay, it won't be the best one, but let's actually try and see what this model will give us. Okay, let's say the model is equal to keras.sequential. So sequential, this way is exactly the same here, but it's good for training to do it a few times. So go in here and say we specify keras.layers.conv, right? So in this case, we don't need to flatten the data. This time we're gonna use convolutional neural network, and this means that we can use images, right? So with the image height and width, so that's fine. So conv2D, so it's 2D, convolutional network for images, and then we specify, for instance, let's say 64 color channels. Well, in this case, it's not color channels, so 64, here we go, filters, here we go. That's always helpful, right? So we got 64 filters, which then, well, stride our network. Then we need to define a kernel size of those filters, let's say 3. In this case, that simply means the size of those 64 filters, which we let, well, move over the image itself, will be 3. And then, of course, we also need to specify an activation function. The stride, as you can see here, by default is 1, 1. It simply means it moves. So each of those filters moves 1 pixel at a time. So if the stride is 1, of course, you can adjust this stride to 2, that basically this filter would move 2 pixels or 3 and so on. So you can really play around with these different kinds of options here. So let's say we start with 64. Let's say in this case 3. For the kernel size, the strides will be as default ones, and the activation function will be, again, it's the relo, right? So relo, but this time, because it's the first layer, we need to specify the input shape. So let's say input shape here is equal to, and now we specify 300 by 300 by 1. So why this input shape? Simply because we already know that we got images of 300 pixels width and 300 pixels height, and the color channel is 1, right? So if you would have 3 color channels, like RGB images, then of course you need to specify 3 here. But remember, at the beginning, we converted in the NumPy array, and we only kept 1 color channel. That is why I'm using the 1 in here, right? Okay, so because we only got 1 color channel. Okay, so we got this. Then we can close this here and add the next. In this case, let's say an additional convolutional layer. So let's say keras.layers.conv2D. Conv2D, here we go. And then we need to specify, in this case, the filters again, the amount of filters. I will do the same approach as I've done here. That's something which is often used, that you basically go down with those filters. Sometimes you see that you start with, for instance, 64, then you got 128, then you got 256, and then you go down again, okay? Different kinds of approaches, but this time here it's our first convolutional network, so it's an easier way, or easier approach. So you simply use only 2 convolutional layers, let's say conv2D, use 32. Again, we say we got 3 as our kernel size for those filters, and then we simply specify the activation here. In this case, I'm referring to redo again, okay? And this time, for the second layer, you don't need to specify the input shape anymore. This is something which is also only required in the first layer. And if you do it like that, up there, it's not required, because flattening simply means that we flatten the data. So there's no need to specify the input shape in here. Okay, so we got this for the second convolutional layer, and then we simply say keras.layers, and now we say flatten. So as soon as you want to move from convolutional layers to dense layers, you need to flatten the data first, because the dense layer only accepts flattened data, so one-dimensional data. So then we specify keras.layers here. Let's go down here, keras.layers, and now say for those .dense, Again, in the last layer, we only need 3 different kinds of neurons because we got 3 output classes. It's a multi-classification problem. That's why we specify 3 here. And then we simply say the activation is equal to softmax. Max, like that. Okay, so we got this as well. And then we need to close the network here like that. That's totally fine. We compile it, model.compile, compile, and then we simply specify the optimizer. Let's say optimizer is equal to Adam. Then we simply say that the loss is equal to keras.losses.sparse category cross entropy. Here we go. This one here, and parentheses, because of course we want to call them. If you want to specify additional parameters here, you can do that. For us now, that's not the case, so I go with the next here and specify the matrix. The matrix is equal to, and again, it's the accuracy, which we want to measure, okay? Because we got a classification problem. Okay, and then we can fit this model. Let's call it history again. History is equal to model.fit. And by the way, you don't need to call it history. This is something which is often used, at least from as far as I know. You can use any other kind of name to store this in that. You don't have to store it anyway. You can also only call model.fit if you want, but I like to store it here. Of course, this especially helpful if you want to plot something later on. For instance, if you want to plot, using matplotlib, for instance, you want to plot the development of the loss over the different kinds of training epochs, or if you want to visualize the accuracy, how it changes over the training epochs, then you can simply refer to history.history and then accuracy, for instance, or history.history and loss if you want. So, okay, let's call it fit, model.fit. And again, I'm referring to my train images here, and then also to the train labels, like that. We specify the epochs, so let's say 5 epochs here in this case, and a batch size. Batch size is equal to, and let's say 32. Okay, so that's it, and let's actually run this. And let's take a look. The training is going here, epoch 1 of 5. And you can see that that probably takes a little bit longer. Let's just see. Okay, it takes a little bit longer, as you can see here. And that is why I will cut this video now, because I don't want you to wait until we are done with the training. I'll show the result in the next video, where we also then try to improve our convolutional network a little bit more. Okay, so that's it. As always, thanks a lot for watching, and I can't wait to see you in the next video. Until then, best guys.